This lecture 22 builds upon some concepts similar to the previous lecture, lecture 21, that was about trace. So we have the notion of eigenvalues of an operator and the complexification of an operator. Complexification is convenient even to study eigenvalues because complex operators, they have as many eigenvalues as the dimension of the space if we count multiplicity, and real eigenvalues, real operators do not have that property. Also, the definition of characteristic polynomial as the product of z minus lambda j for every eigenvalue lambda j of the operator, or in fact of the complexification of that operator, so that if we list here in this product the eigenvalues with their multiplicity, the degree of this polynomial always equals to n, where n is the dimension of the space. Now also, from a long time ago, what is a change of basis? So when we have a certain basis for a finite dimensional vector space and we have an operator on that vector space, then we can write a matrix A that represents that operator with respect to that basis. And if we want to consider a different basis, then we get a different matrix, which is obtained by simply multiplying A from the left by some invertible matrix I call here Q, and from the right by another, the inverse of this matrix Q. And another property that only complex vector spaces have is that for every operator on a finite dimensional complex vector space, it is possible to find the basis for which the operator's matrix is upper triangular. And when we see the proof of this fact, just like the fact that operators have n eigenvalues and that it's always relying on the fundamental theorem of algebra, that's where these properties come from, and this is why complex vector spaces have these properties and real vector spaces don't. And there is a very long proof that we have seen already in the Honors Linear Algebra 1, which is that the determinant of the product is the product of the determinant. We did not reproduce this proof in this lecture, we just used this. And finally, for some more fancy and sophisticated applications of the notion of determinant, let's remind what is an isometry. An isometry is in a inner product space. That's a space where we can actually measure vectors by defining a norm as the square root of the inner product of the vector and itself. And an isometry on an inner product space is a linear map with the property that it preserves the norm. A positive operator, again, let's recall that's an operator with the property that for every vector, it will map this vector to another vector, maybe possibly the same, maybe even zero, which is on the same side of that vector with respect to the orthogonal complement of that vector. So if we take a vector, we look at the hyperplane or the subspace of all vectors orthogonal to it, and we look what's the image of this vector under T, it's on the same side of that hyperplane, it's not on the other side. This is a positive operator, and an equivalent formulation is it is self-adjoint, and all eigenvalues are non-negative. That's what we call positive operator in this course. Finally, we saw the singular value decomposition many lectures ago, which says that on any real or complex finite dimensional inner product space, any operator on that space, we can write that operator, a matrix of that operator, as a diagonal matrix with non-negative entries. Let me here on the diagonal, I call these entries not lambda, I call them S, S1, S2, S3, up to Sn. with a serious drawback, which is that the input bases and the output bases, they are not the same, but they are orthonormal, which is very important. So these are orthonormal bases, both of them. This is a fundamental property of singular value decomposition. And again, these numbers here on the diagonal, they are non-negative. And it is true that it's quite inconvenient to have different bases. Well, if they were the same bases and they were also orthonormal, we would be talking about self-adjoint operators, which is a very small class of operators. And the singular value decomposition, the power of it is how general it is. Here, this is true for every linear operator on a finite dimensional inner product space. And we're also going to use it in an important way when we relate the volume, how an operator changes the volume of regions in the Euclidean space to its determinant. The lecture starts by defining what is the determinant of an operator. What is the determinant of an operator? Well, first, if the space is real, we complexify the operator. Now it has n eigenvalues. Maybe with multiplicity, we multiply those eigenvalues, and that's it. That's what the determinant of an operator is. Then we saw that the characteristic polynomial of an operator was nothing but the determinant of z times the identity minus the operator, where z is, of course, the variable, the dummy variable in the expression for this polynomial. Recalling that in this course, we defined the characteristic polynomial as the product of z minus lambda j over all different, or maybe not different, with multiplicity eigenvalues lambda j of the complexification of the operator. So this theorem that we proved, it's reconciling both these two definitions of characteristic polynomial. This one and this one, they are the same. Then we briefly recalled what is the definition of determinant of a matrix that is back from Honors Linear Algebra 1, and we had not used this at any point in this Honors Linear Algebra 2 course so far. And using this property that the determinant factorizes, and when we have a change of basis, which means multiplying the matrix from the left by a matrix and from the right by the inverse of that matrix, because of factorization, you can also commute. So the determinant in the end does not depend on which basis we choose. And because we can choose a basis which makes the matrix upper triangular, we have this identity. The determinant of an operator equals the determinant of its matrix. Even if these two come from very different definitions, then that's a theorem. They are the same, and it doesn't depend, it doesn't matter which basis we put here, we'll always get the same number. Finally, by combining properties of isometries, positive operators, and singular value decomposition, we proved that this beautiful relation that makes linear algebra a fundamental piece of multidimensional analysis, and that's the volume, how a linear operator changes the volume of regions which are subsets of the Euclidean space. And we proved this. Of course, we made some assumptions. There are some details there. In particular, we assumed that the volume of region could be computed by approximating that region using either rectangles like this, or we could also approximate the volume of a region by filling that region with balls like this. And this was very important to use both definitions. One of them was important because we didn't want to use any analysis or any complicated epsilon delta. This was a very soft argument. We just took for granted that these two definitions give the same number. And then for balls, it is easy to prove then that isometries preserve volume. On the other hand, for rectangles, it is easier to prove that positive operators, or more precisely diagonal operators, they stretch volume by a factor which is given exactly by the absolute value of its determinant. And that's how we got this beautiful formula here. Some students pointed out that the volume part of this lecture, it required some analysis. I would say it required really very little, given that what I just said, it took for granted that volume could be computed using either rectangles or balls. So you just had to play a tiny little bit with the definition of inf when we change the volume a little bit and see what properties of the infimum were being used there to in some of the identities of the many identities that we proved towards the proof of the main property, which was that the volume, that a linear map stretches volume exactly by a factor given by the absolute value of its determinant. Other students pointed out that the lecture, this lecture 22, combined some knowledge of trace, and I would say there is hardly any connection with what we saw in the previous lecture, except that it all feels similar. There's a big parallel that what we're doing, looking at eigenvalues, complexification, and defining things in terms of the eigenvalues. Other student mentioned that an operator, the determinant, describes how a linear operator will stretch space. And I think the determinant is a very good tool, but it doesn't go that far. It doesn't describe completely how space is stretched. In order to know that, you have to look at the linear map entire definition, all the structure, all the information there in the linear operator. What the determinant does, that is true, is that it tells what is the net product in terms of volume. If you measure the volume, then the determinant, it tells you exactly by how much it changed. So maybe you get some original object that looks like this, and then you smash it, and it now looks like this. So the determinant doesn't tell you exactly all the details of what happened here, but it tells you how the volume of the image relates to the volume of the original object. Some student mentioned that the determinant is preserved by an isometry. I don't know exactly what that would mean, to preserve, but if that means the determinant of an isometry composed with an operator t is the same as the determinant of the operator t itself, this is not entirely true. It is true only if we put absolute values on both sides, but in general this is not true. And the reason is exactly of what another student said, which is that the determinant of isometry is equal to 1, and that is not true. The determinant of an isometry, if the space is complex, it can be any complex number whose absolute value equal 1. If the space is real, it can be any real number whose absolute value equals 1, so that is of course just plus 1 and minus 1 when the space is real. But then otherwise there is an entire circle where the numbers can be if it's on the space of complex. One student said that in this lecture we proved the infimum definition of volumes. I don't think we can prove a definition. What we did is we gave a definition of volume by taking the infimum of unions, countable union of balls or boxes, rectangles that cover a region, a bounded open set in the Euclidean space, and we proved properties about that volume defined that way. Finally, another student mentioned to me that the definition of volume is abstract and hard to apply. I would agree that at this point the definition of trace, if we make a parallel, is harder, abstract, and not so clear how it is applied. But the definition of volume that we have, This is what you see in every course of mathematics you take in the future. This is how you define volume of an open set. Is really you take some elementary object that you already know how to measure, and you cover your funny region with objects like that, and you try to make this covering of your object as economic as possible. And when we say as economic as possible, it means you take the infimum of over all possible ways to cover, so you try to make the waste, so to say, as small as possible. So this is really the notion of volume that is used in mathematics.